Russ can take it.
Oh boy. All right, are we ready to go, Dr. Davis?
Ready when you are.
All righty. So my project was on atomic force microscopy. So here's a pretty basic schematic for AFM that I made for my infographic. So this is the table where the sample would sit. So I guess I could start off by talking about how, like, what atomic force microscopy is used for. That's at the top of my infographic. Um, it's basically used to look at um, topography and physical properties of nanosurfaces, so sample surfaces at a nanoscale. So it does that by using this basically arm, this cantilever that has a tip attached to it that comes close or in contact with the sample surface. This tip is often made of silicon or silicon nitrate material. And then there's this laser that's shined on the back of the cantilever arm and reflects to this 4-zone diode. It's initially set up so that the reflection of the laser makes contact with the center of this diode. And as this, the tip on the cantilever is moved across the sample, it changes the deflection of the laser and will move the position of the laser into one of the other 4 quadrants as it either moves up or down, depending on the topography or the physical interactions of the nanosurface. So then this is, it goes to a computer, so the computer can tell where the light is shining on this diode, this photodiode, and then it gives feedback control to the sample. It's controlled by it's a piezoelectric component. So the stage is moved based on electrical current, either expanding or contracting the sample stage. And so this moves to, after a change in the position of the tip and the cantilever, it moves the laser back to the center so that it can then record when the tip drops back down or increases further. And so this feedback control happens throughout the whole scanning period. And so you're able to eventually build a 3D model of the surface that you're scanning using AFM. This little graph that I included down here, this is what Dr. Arrington calls the most important image in chemistry. And so it's talking about how when you bring 2 atoms closer together, as so far apart, there's no interaction occurring. And as they get closer and closer together, they start to exhibit attractive forces. And as they get closer and closer together, they then start to exhibit repulsive forces. So this is, the AFM follows this fairly closely. And so when the tip is in direct contact with the surface, you get these strong repulsive forces. As it moves away from that surface, you start to get those attractive forces, and then until you get to complete separation. So some of the uses of AFM, like I said, you can get the size, the texture, roughness, the surface area, or the volume distribution across a nanosurface, so at a nanoscale. It's really good at constructing 3D pictures of surfaces. So that's one of the advantages of using AFM, is that you can get a 3D picture of the surface, such as like these human chromosomes, or looking at the volume distribution or the size of these nanotubes. You can also utilize these cantilever tips for surface manipulation. So you can manipulate the surface of that nanomaterial and put pores or detectors or things on a nanomaterial. And then you can also use the force measurement of that tip based on the graph that I showed previously. And that's how you can determine some of the physical and mechanical properties of the nanomaterial that you're scanning or looking at. So there are two main methods of running an AFM. One is a contact method, which is on the right, showed on the right-hand side. This is where the tip of the cantilever arm is in contact or very close to the surface throughout the entire scanning period. And so this is the less common method. It's mostly used for looking at the linear force readings from the AFM. The reason this is less common is because it can damage the tip or the surface that you're recording. And so it's a less rugged method. The tapping method on the left-hand side is more common. And based on the signal, it vibrates the cantilever arm to get the same sorts of measurements, but the tip is not always in direct contact with the surface. And so it still uses that feedback loop and the four array detector, that 4-zone photodiode, to record the interactions to record the force interactions between the tip and the atoms of the nanomaterial below it. So a few figures of merit. There's a vertical resolution of less than 0.1 nanometers, a horizontal resolution, so in the X and Y direction, of approximately 1 nanometer. Based on my research, it said I couldn't find any like actual numbers for the cost of operating this, operating an AFM, but it says it was very cost effective compared to other forms of nanoscale imaging. When I looked on the Bruker manufacturer's website, they claim that they have that there's fast scanning and repeatability, especially with their Dimension Icon XR instrument. And so there's low noise and drift, so you're able to get pretty precise measurements and imaging from their instrument. And then, as I mentioned earlier, the ruggedness of the tip that's on that cantilever arm is of concern. But using that tapping method and stronger tips usually helps get around this. So looking at other instruments, the one that I looked at when comparing AFM was the scanning electron microscope. So with an AFM, it has a greater lateral resolution. So in the X and Y direction, it can give a better image, but it does lack the depth of field that's capable on a scanning electron microscope. So its resolution in the Z direction and the amount that it can vary in the Z direction is not as good as on a scanning electron microscope. One of the biggest advantages for AFM is that its imaging and scanning can be performed in an air medium, a liquid medium, or in a vacuum, whereas the scanning electron microscope often requires a vacuum for optimal operation. The AFM measures physical properties of a surface, so this includes the magnetic field interactions, the friction, thermal information, and surface potential. But it can't tell any chemical composition information like in a scanning electron microscope. So you are able to get a lot of those physical properties from the nanosurface that can be very valuable, but you can't actually get any of the chemical information from the material. The biggest advantage, I think, of the AFM is that you get 3-dimension magnification, so you can build that full 3D image, whereas with the scanning electron microscope, it's only capable of magnification in 2 dimensions. And then another advantage of AFM is that it does not require samples to undergo special treatments. So you're able to just sort of lay the sample, you lay the surface sample and then use the AFM. You don't have to give it a special coating or treatment that could possibly damage the sample. So the sample prep is pretty minimal for AFM. So as you, I guess you could have guessed, AFM is very important for nanoscience experiments and building nanomaterials such as like nanotubes or nanoparticles for drug delivery. And AFM can also be used in conjunction with Raman spectroscopy. So I found a few instruments where AFM and Raman spectroscopy were built in. And so that way you could gather information both about the physical properties of the nanomaterial and also some of the chemical composition and vibrational information. I included my exam questions in my presentation, since you said we'd probably share them with each other anyway.
Yep.
So this question, which of the following is the reason you would not want to use atomic force microscopy? And so if the surface has a wide vertical range, you wouldn't want to use AFM. You'd want to use something, I guess, more like scanning electron microscopy, since the atomic force microscopy doesn't have a wide vertical range, whereas it can take place in liquid. It can be used to measure magnetic field, and it can be used to manipulate the nanosurface. And then what are the two detection modes in AFM and what is an advantage of each? So contact and tapping mode. So the contact mode is good for linear force readings, and the tapping mode reduces the stress on the tip and surface. And then my resources.
All right. Any questions for Russ? So I used AFM during an undergraduate research project, and those tips do break easily. When you're an undergrad and you break a $20 tip, it seems like a big deal, but in the scheme of things, it's not that big. When you break 3 in a row, you feel bad. And as a grad student, I dropped a screw in a $30,000 pump, and they were like, and I said, okay. All right. Well, thank you, sir.
Yes, sir.
Next on our list is Abigail.
Okay, I've never shared a screen before.
You should have a green button at the bottom of your Zoom window.
Okay, can y'all see that? Okay, so capillary electrophoresis. So to start off with a little bit of background, it's a relatively new topic or mode of analysis. It was used as, electrophoresis at least, was used as early as the 19th century, but it didn't really get a lot of credit until the capillaries were introduced in the 1960s by Cureton, and that is an essential part of what makes the process so efficient. It was proved to be able to separate proteins in 1930, but it wasn't made commercially available until the 1980s. And so that's a big reason why, that's a big part of its disadvantages, is that it's not quite as developed as some other techniques because it is relatively recent. So this is the schematic of the system. There are many different types of capillary electrophoresis, and they have some changes within this, but they all generally operate under this system. So there is a power supply that puts in a high voltage up to 30 kilovolts into the system. And then that voltage is carried through to the electrodes at both sides, which carry the power throughout the whole system. There's a narrow capillary tube in the millimeter scale, which runs through from one electrode to the other. It is first flushed with a buffer before it's introduced to the sample, and then the sample is injected either by pressure differences or by applying a volt. And the sample is very, very small. It's 1 to 10 nanoliters as opposed to microliters in HPLC and other techniques. So that is an advantage that I'll get into later, is the small sample size. The capillary tube is often made of fused silica. It's very narrow, and the design of the very narrow tube and the thin walls creates a high surface to volume ratio, which eliminates overheating from that high power supply. So that's another advantage that I'll mention again later. There can be a small window near the cathode end of the capillary, and that allows for UV-vis light to enter and absorbance measurements to be made. And another adjustment that can be made is a photomultiplier tube can be added to the cathode end, and that can allow for mass spectrum measurements to be made. The negatively charged silica wall attracts to the often positively charged buffer, and that allows the sample to flow through easily. And the detector at the end, it can measure many different things. You can get a range of data from this, but it most often measures absorbance, but it can also do fluorescence, mass to charge ratios, and things like that. So this is just an example of how the data would look. This is from a journal that studied separation of peptides through capillary electrophoresis, and you see time on the bottom. There is a relatively quick time for this technique, often 1 to 20 minutes, as opposed to up to 30 minutes for HPLC, and absorbance on the y-axis. So some advantages of this method is a lot of it comes from the capillary tube, and the way that it is designed gives a lot of advantages to the process. Again, the surface to volume ratio reduces overheating, which also reduces deterioration of the sample and encourages reproducibility. There's lateral diffusion effects are reduced, which is often a problem in HPLC, which is the most comparable technique of analysis to this technique. This technique has a plug flow. The velocity is consistent throughout the tube, and it's not slower at the edges of the walls, which could create a bulge in the center, which could create problems in other techniques. Other advantages is the small sample size. Again, it's in the nanoliter scale as opposed to microliters for other techniques, and the quick runtime, 1 to 20 minute runtime, and only about 5 minutes at most for the buffer equilibration time. And this is a reference of the different flows that you'll see in HPLC versus CE. There's flat flow in CE as opposed to parabolic flow, and that creates higher resolution, higher selectivity, and gives clearer data than you would get in HPLC. So some disadvantages: the temperature and pH is essential to the system. It must be held constant, and that can create some issues, and it requires some more instrumentation. Some CE methods have a temperature control gauge, but it's, again, not as prone to overheating from the supply because of the capillary design. There are limited detector options, and instrumentation is not widely available, again, because it's such a new technique. It hasn't been developed as much as the others. And for that reason as well, it isn't as mobile. These are the 6 types. The most common is the first, capillary zone electrophoresis, but there are several others, all which have slight adjustments to the system that allow it to measure different things or measure them in a different way. But I'll get into some of them briefly. This is the breakdown of the types of systems, all 6 that were listed before, the most common being CZE. A discontinuous system is one in which it keeps the sample in distinct zones separated by 2 electrolytes, but continuous system is obviously the most common. It has a background electrolyte buffer that runs consistently through the capillary while the sample runs through as well. And then kinetic processes have a constant electrolyte composition, whereas steady state processes have varying electrolyte composition. So CZE is the most common. It's also called free solution capillary electrophoresis. Separation is based on the differences in electrophoretic mobility. And probably the second most common is capillary gel electrophoresis. Separation is based on the difference in solute size alone, not charge or mobility. Gels minimize solute diffusion that causes band broadening and other techniques, and it limits heat transfer between the molecules, which keeps the temperature stable, as I said, was so important to the system. So these are some applications. This is what it would look like in a lab. This is a Beckman-Coulter model. Some popular applications are definitely in biochemistry, with DNA fingerprinting, drug analysis, the separation of large molecules and proteins allows for CE to detect blood disorders. For example, monoclonal immunoglobulins are present in very low amounts with people suffering from leukemia or lymphoma. And so this technique can determine the concentration of certain things in your blood and then be able to help in diagnoses. Also, food evaluation is a huge one. Forensic toxicology, it can detect illicit substances in urine or blood, and it can be used to analyze drugs in the blood as you're being treated to prevent overdose or toxic side effects. There's many applications in the real world, and though it isn't quite as developed as some other techniques, as it grows over time, it could be one of the most beneficial techniques in chemical analysis. So these are my exam questions. I also put them on here. Both open-ended. What advantages does capillary electrophoresis have over HPLC? The prevention of overheating, the shorter runtime, the smaller sample size. There's many options you could say for that. And how does capillary electrophoresis analysis prevent overheating and deterioration of the sample? Like I said before, with the capillary design, the surface to volume ratio is increased, which prevents overheating from the high power source. And my sources, and that is all. I don't.
All right, any questions for
Sorry.
Abigail? Those of you that did research with Radford, does he have a CE? Did you use a CE? No.
I don't remember. I remember electrophoresis stuff.
Mm-hmm. But not capillary electrophoresis.
Capillary.
When I did research with Dr. Radford, I don't believe I did that.
Okay. I know that he has talked about getting a CE. I just don't remember if it was on his wish list or if he has already gotten it. They're not inexpensive. Abigail, I do have one question, and I don't know if you found this. I've never run a CE. Do they talk at all about the difference in pressure between like an HPLC pump and a CE pump? Or
Yes, I did. There was, in one of the journal articles I read, which is in my sources, there's a whole section on it. I think maintaining pressure wasn't as much of a concern in capillary electrophoresis. I'm not totally certain why, but I think I know that pressure differences are a common method of injection in CE, but I don't think the pressure of the system is like a vital component.
Okay.
Necessarily.
Sure. Yeah, I mean, I know most of the movement happens due to the electrical current rather than due to the pressure. But I didn't know if it talked at all about what those pressures were.
I can definitely get back to you on that.
All right, excellent. Third on the list is circular dichroism. Baja.
Oh, that's me. All right. Before I begin, if you hear a dog barking, I'm sorry. I have no control over that. But let's do this. All right. Oh wait, you gotta share screen. Here we go. This one. All right. Everyone can see anything? Everything's good? All right. So circular dichroism spectroscopy, that was my chosen instrument to learn about. So I guess we'll jump straight into it. So what is like, before getting into like the instrumental designs and stuff, what does the circular dichroism look at particularly? Well, it works on, it's same as in general spectroscopy where it looks at the absorbance of molecules absorbance, but in this particular case, it looks at the absorbance of circular polarized light, which is commonly seen that of chiral molecules or optically active molecules that absorb circular polarized light. And with that in mind, these circular polarized lights have certain rotations to them as they move through their propagation line as they travel, as they have like a constant magnitude of E, and it rotates around that axis. And the type of molecules, these optically active molecules, they absorb these polarized lights in both the, you could say, right or clockwise circular polar light rotation, or left counterclockwise circular polar light rotation. And they absorb these at different amounts. It's different between the left and right absorption hand of these optically active molecules. And this difference can be used to determine the identity of these certain chiral molecules. And because of this, we can also apply Beer's-Lambert law to analyzing these chiral molecules. As we can see over in this top right corner, we have absorption equal to the molar extinction coefficient times the concentration times the path length. We can set it up like further down where we have the absorbance of the molecule of the left circular polarized light, and we can subtract that from the absorbance of the circularized light from the right orientation. And we can set that absorbance ratio and make it equal to the expression of the molar extinction coefficients between the left-handed circular polarized light rotation and the right-handed circular polarized light rotation. And with this correlation, we can set up a graph that can analyze how these absorption coefficients can change depending on the wavelength of light that travels through and the concentration, path length, similar to the Beer's-Lambert law. So that's very useful for identifying the molecular species for chiral molecules or optically active molecules, and for CD instruments in particular. They usually need to be optically active, or they can be induced to be optically active. But for the most part, they use optically active molecules. So for a schematic that I designed on Word for the CD design, you have an intense white light, unpolarized light source that will travel through a filter wheel. And the filter wheel will select for a wavelength, like a monochromator, a desired wavelength of choice. And that wavelength of light will pass through that filter wheel, but still unpolarized. So similar to a polarimeter instrument, it'll go through a polarizer, which will to change the light to polarized light, but the polarized light is linear, meaning that there is no rotation around an axis. It's just the energy is only in one plane. So for this to interact with the chiral molecules, it needs to become circular polarized light. And that's where you have a photoelastic modulator, or PEM, that it will travel through and induce the linear polarized light to change into circular polarized light. And then after that circular polarized light will go through the sample, and the counterclockwise and clockwise rotations, left and right, will be absorbed at different amounts by the sample of the chiral molecules. And whatever passes through will get to the detector and go through the computer, and we can analyze the change in absorbances between the two, which can be used to further calculate a spectra diagram to analyze what it is we're looking at, particularly by looking at already representations of previously referenced spectrums. So what is this like used for? So circular dichroism, generally its major uses in like biology or biochemistry, where it's analyzing the structures of proteins. And in terms of secondary structures like beta sheaths and alpha helices and the Ren coils and whatnot, because those structures, chiral molecules, biological molecules in general are chiral. So they are optically active, which is very useful for circular dichroism. And so when you're analyzing these secondary protein structures, you can put your sample and run it through the circuit CD and see how its spectra correlates to the reference spectra, and see, okay, what does it look like? If it has a similar peak to, let's say, this red peak, we would say there would be maybe like a majority more of alpha helices in this protein structure. Some other things you can look at based on the types of CD instruments you can use. There's metal ligand complexes, where you can look at the metal interactions with certain biological molecules or protein structures or optically active molecules, or just ligands in general. But if the ligands in the metal complex is not optically active, you would have to induce that activity, and there's an instrument for that I will get to later. But another useful thing because of this CD application is that you can also visualize the change in the protein structure over time as you're analyzing the secondary structure. As with like time, maybe in temperature, the protein structure can change. Maybe the alpha helices will uncoil, the beta sheaths will unbind, and that can affect the spectra that you see. And so you can run kinetics and thermodynamic studies with the CD instrument to visualize this. So in a topic related to today, for a journal I found this particular instrument. It was called J1100, which is a CD. And this company, they funded the research for this particular, for COVID, I guess, to make it their device more appealing to purchase as of right now. And what they looked at was this antibody, VHH, which is like I won't get into the biology, but it's an antibody. It's a protein, and it's against COVID-19. It binds to this glycoprotein structure, another protein structure on the SARS virus. And that's they wanted to analyze like the stability of this protein as you change temperature and see how well you can do it, like store it and such and whatnot. So in the top right corner, you have various samples of this antibody, and they look at its absorbed spectra, like before heating it and after heating it, where before heating is the blue and after heating is the red. And they're seeing how that change in the absorbance spectra will relate to the denaturing of the protein. So you can see how stable the molecule is as you increase temperature. And these 25 and 65 and 73 degrees C is the starting temperatures that these molecules started at before heating up. And so we can see how the temperature affects the stability of the molecule. And down below, we have a temperature study where they heated the antibody and then they cooled it to see how it could reverse the structure, refolding aspect. So a lot of the times when you denature a protein, a lot of the secondary structures will unfold or unbind. But if you recool it, sometimes it can reverse. That reaction can be reversible, in which case you can have recoiling, reformation of the alpha and beta sheet, alpha helices and beta sheets. And they wanted to see if that was effective in this research. And in conclusion, they found that these antibodies were very stable in some ways of reforming beta sheets and alpha helices for temperature changes, which I thought was very interesting. But moving on, some like types and related CD interpretations, where a lot of these circular dichroism or CD interpretations are used to analyze biological molecules because of their chiral activity. And so a lot of secondary structures are around the 200 to 280 nanometer range, which can be used for either far UV or near UV. I believe far UV CD is used for analyzing secondary structure, protein structures, and then near UV CD is used to analyze tertiary protein structures. And then the visible CD is used to analyze, I believe, the interaction between metals and proteins. And oh yeah, I mentioned earlier about how some molecules that are not optically active cannot be used with CD interpretation. Well, you can use magnetic circular dichroism to, it induces a magnetic field onto the, I believe, parallel to the light, which will induce optically active molecules that aren't optically active to become optically active. And in that case, they usually analyze, I believe, metal to ligand interactions. So I wanted to take this time to also talk about advantages and disadvantages of CD by comparing cellular dichroism to NMR spectroscopy, where they're both in essential analyzing molecules, where NMR is more of looking at a small scale and CD is more looking at a big scale. And so with that, a particular advantage for CD is that they can analyze large molecules like proteins in general. They have general analyzation where you can determine structures of this protein in terms of what components it's made up of, like alpha sheets, beta sheets, alpha helices. But with NMR analysis, you tend to not, you can't really analyze really large molecules like proteins because you can have issues like peak overlap between components that you can see. Another useful thing about CD is that they're capable of distinguishing between enantiomers because of the difference in absorbing left and right-handed polarized light as a factor of chiral molecules in general. But with NMRs, you can't really, it's difficult or near impossible to distinguish enantiomers. I believe there's a way, but I didn't look into that way specifically, but I did find that generally that the peaks are usually the same for enantiomers. And with that, NMR is you can be used to specifically identify structures, like these small structures, identify what's on them, what components based on the the neighboring protons and whatnot. While as in CD, you can't identify the exact structure of it. It's more of a generalized identification, qualitative analysis, where it's like, okay, what percent of this protein molecule has secondary structure? What percent is what percent is alpha helices? What percent is beta sheets? But another issue of CD is that there's some major solvent effects that you have to take into account when setting up the instrument and setting up the experiment, because for some factors for the solvent that dissolves the sample, you need the sample to be soluble in the solvent. You need the solvent to be optically inactive. You need the sample to be stable in the solvent over time. Otherwise, your data will change over time. And you need to degas the solvent from oxygen, because the oxygen, I believe, can be picked up in the wavelengths around the 200 nanometer mark, where a lot of those secondary protein structures are, which can affect the spectrum that you pick up. But in general, though, the CD instrument is very fast in analyzing, the kinetics of these protein changes, because you can analyze it as temperature changes over time, and you can compare that. Whereas in NMR spectroscopy, it's more difficult because of the amount of time. I believe with CD, you're looking at I believe it's called the UV spectrum, where NMR is like the vibrations of radio waves, and CD is faster in that respect. But NMR is more specific in general with identifying structures. So in conclusion, I would say that CD is very useful for identifying large molecules compared to NMR, very fast. And depending on the type of instrument you can buy, you can set it up so that it is also very precise and accurate and low signal to noise ratio based on additional like components that you can add, such as I believe it's like a nitrogen gas thing that will like flow out any excess oxygen to prevent contamination. Yeah, and so that's my works cited. And thank you. If you have any, I don't have my questions on here, I will email them to you. But it's probably going to be like a question of like calculating the molar extinction coefficient from like, I gave you absorbance or something. And I'll talk about like, what would a negative value indicate about the amount of light absorbed from the left versus the right. Yeah, I'll email it to you after this. Yeah.
Excellent. Excellent.
Yeah. Any questions? Thought the circular dichromosome was really cool. I didn't think it was about like this, the analyzing protein stuff. I just picked it because it sounded cool, circular. But you know, that protein stuff was really cool. Very fitting.
Do you know what path lengths they use? So, I mean, you know, 170
yeah.
is
So
standard UV.
Yeah, so the path length, it can vary depending on like the concentration you use and whether because you can increase the path length if the concentration is too low to get the absorbance reading high. That's what I read about. And so it's based on the concentration, but for exact numbers, I don't remember, but.
Yeah, I know that there can be issues if water is your solvent. There can be issues down in the far UV.
Yeah.
But.
Yeah, there's also another factor with solvent. There's a lot of solvent effects that affect it. I think another one was like transparency too, like the light passing through it in terms of reflecting. You want it to just go through the optically active molecules without interacting with the solvent itself.
Yeah. I don't know if you remember back in chapter 3, it's been a while. There was a question about the NBK7 glass, and it talked about the refractive index versus wavelength. And the curve was almost logarithmic in terms of its decay, right? And so at shorter wavelengths, the fraction, the index of refraction is larger than at longer wavelengths because at shorter wavelengths, if you think about it, is more of the wave is actually interacting with that surface, right? If the width of that surface interaction is close to the wavelength versus if it's a real long wave that's passing through that surface. And so as you get down to these very low wavelengths, 190 nanometers, which is what we're looking at with CD, you can have huge indices of refraction. And so usually they want to minimize the surface differences between your solvent and your cuvette as well. I did have one question about one of your graphs. You don't have to reshare your screen unless you really want to.
I can do it.
I think it was on your COVID study.
Ooh, okay.
Yeah. The y-axis had units of MOL, ELLIP.
Yes. Where's that? Yes, that stands for, it's another term for degree of ellipticity. And so I can go back to this term right here, this theta looking symbol, degree of ellipticity. So another way of graphing these spectra, instead of using the molar extinction coefficient is that you can calculate molar degree of ellipticity. And ellipticity is related to circular polarized light. It's very complicated. It looked very confusing, but it's kind of like, it looked like it was changing the orientation to more of like a linear a polarized light direction. From what I got from it in general, in terms of what I know, is that this is the equation that they use. They're calculating molar or degree of ellipticity, and they use degree of ellipticity in some graphs for some spectra that they use. They either use the degree of ellipticity or they use molar extinguished coefficient for these graphs.
Okay.
And so
is that 3,300 a constant?
Yes,
okay.
Yes. I don't know how they derived it though,
sure.
but yes.
Okay.
So I might have a math question with something like this. Yeah. Okay.
All right. Very good.
Yeah.
Next on our alphabetical list, EPR. I think that's Caroline.
That's me. All right. Here we go. I have a game to start us off. Maybe. Wait.
Jeopardy?
Not Jeopardy. I'm worried about the time limit because I can get long-winded. Okay. Okay. So we're gonna start with the game, like I've already said. Kind of jog your memory a little bit because I always have to remind myself these terms before I talk about them. So which one of these, the left or the right, would we call paramagnetic? You can unmute yourself.
Is that where there's unfilled? Is that filled or unfilled? Diamagnetic, paramagnetic.
Yeah, it's difficult. So remember, di means two. So in diamagnetic systems, all of your electrons are paired. They have a buddy. In paramagnetic systems, you have unpaired electrons. No, okay. Can I use my ear? Yes. All right. So the next question is, which of these will we call an open shell system as opposed to a closed shell system?
Paramagnetic?
Yeah.
Is that open shell?
Yes, exactly. So I'm going to refer to systems as paramagnetic and open shell, and I wanted you to know what I was talking about. Okay, so now we have a good basis for learning about electron paramagnetic resonance spectroscopy. When you look at this name, you see magnetic resonance spectroscopy, and fire alarms should be going off in your head because we learned about something where the name sounds very familiar. What would that be?
NMR.
NMR, yes. So I stole pictures from Dr. Davis's great lecture to remind you what NMR spectroscopy is. So if you recall, we were looking at spins of nuclei here, and the information we get from NMR tells us a lot about the environment of the nuclei in our system. So we have a magnet, we have a radio frequency, and also a receiver that are orthogonal to each other. And we talked about how you have your nuclei, and then when you apply the magnetic field, you flip their spins, excite them, and then as they relax down, we get this frequency of precession, yada, yada, yada. Hopefully you already know that, but I wanted to remind you. So what if we could detect the environment of an electron? That'd be really cool. And you can't use an NMR for that because it's an NMR, but an EPR goes off the same theory in general and instrumentation of NMR, but now we're applying it to electrons. So in NMR, like we just talked about, we were, the spin of the nucleus really helps us out a lot, right? It produces that frequency. It's what we need. So let's talk about the spin of an electron. So I'm sure you already know this either from Jen Kim or Dr. Arrington or somebody, Dr. Davis. So we have an intrinsic angular momentum. So this is just like a free electron spinning on its own axis. Then you have orbital angular momentum. So electrons are in molecules, right? They're in atoms. They're spinning around nuclei. And so you have both of these happening at once. And that produces what's called a spin orbit effect. Spin orbit coupling. And so spin orbit coupling as a term to go forward, I'm saying it now, so listen up. It's just how these two affect each other, how the intrinsic angular momentum and the orbital angular momentum affect each other and how they couple. So an NMR will not work for systems when we're focused on the electrons only, because electrons have a magnetic moment 2 to 3 orders of magnitude greater than a nucleus. And so we need an instrument that's a little bit more specific. In fact, we need an instrument that has less of a magnetic field and a higher frequency. We're going to take a quick break right here. You can unmute your mics. Why would we call this? Why do we need it to be paramagnetic and not diamagnetic? Why do you think? Think about the electron spinning and maybe a magnetic field.
The spins would cancel out in diamagnetic, and magnetic field, I'm not sure about. Wait, would that?
Yeah, so it cancels out. So if the spins cancel out, then you get no net magnetic field. So when we're looking at systems through this magnetic resonance spectroscopy, we want to have like a resonating magnetic field. And the only way you can get that is when you have a charge spinning and it's not being canceled out. So that's why we can only do this on paramagnetic systems. Okay, for the instrument, this is the EPR. It actually looks similar to the NMR, even if you don't see it off the bat. I didn't see it off the bat, but once I learned about it, it does. So just trust me on that. Your source is normally called a klystron. And we talked about higher frequency. So can anyone recall like the next highest frequency after radio frequency on the spectrum? It's microwave. So that's the frequencies we're using here. And then those flow into the sample cavity. The sample cavity helps retain that frequency. And also, while we're here, I'll talk about a disadvantage of this is that electrons are moving super, super quickly. And so you actually need your samples to be super cold. And when I say super cold, I'm talking like 20 Kelvin. I saw reports as low as 2 Kelvin. So more than freezing. And then also you have your magnet going through the sample. So this is just a more sensitive version. Like I've already said, but I'll remind you, our magnet is less strong, but we have higher frequencies to capture that electronic information. Okay, a little bit of theory, because I love this stuff. You look at the graph and you should be like, wow, that looks exactly like the NMR slide. And you're right, it's practically the same thing. You have the Zeeman effect of the splitting of the two opposing spins of the electron. And what happens is your microwave frequency is set. So we kind of choose normally, I think it's 9.8 megahertz, gigahertz? Gigahertz, thank you, Dr. David. And then we change our magnetic field. So we kind of sweep the magnetic field. And delta U, delta E, same difference. But we have this G factor, which is experimentally determined pretty much and dependent on the system. We'll talk about that in a second. Beta is a constant, and B naught is, of course, the magnetic field. And we're going to get an absorbance as the magnetic field is sweeping. So we'll get a number wherever that absorbance occurs, wherever this G times beta times B naught equals the H nu, our nu coming from our microwave frequency, we'll get a signal. So now I want to talk about that G, because that G is actually very important. So once you run an EPR, you're going to have, of course, we know H plus Planck's constant, we know our frequency, we know beta, and we know B naught because that's where the absorbance occurred. The spectra can have an x-axis of B, of the magnetic field sweeping, or it can go ahead and the computer can do the math for you and you can have x-axis of the G factor because it's a plug and chug system. But what does this mean? That's a great question. So the G value of just a free electron, no nucleus, is just over 2.0023. Deviation in this G factor comes from that spin orbit coupling. So basically, important part is that the larger the nuclei that unpaired electron is orbiting, the more you're going to have an effect from spin orbit coupling. So if we have a G value that's pretty close to 2, then that tells us that our nucleus is pretty small. And so that might be like an organic free radical, carbon, nitrogen, oxygen, something like that. If you have a much larger G value, a larger deviation, then that means that that spin orbit coupling has a greater effect. You have a larger nucleus. You're probably talking like D and F block elements, maybe transition metals, something like that. Another thing that our spectra can show us, of course, we can have this splitting like we have in some other instruments. And this is because the nuclei can affect the magnetic field that that unpaired electron feels. A really neat thing though, is that the hyperfine splitting, you're still going to have your G factor or that magnetic field where the absorption occurs in the center. Can you see my mouse spinning? Okay, so this is the first derivative of the absorption peak so that you can see exactly where it crosses the x-axis. So you can find your B naught or your G factor from that. And then over here, you would look right in between. So even though they're splitting, we can still get good information. So to kind of recap from the spectra, first off, if you get a reading at all, that tells you, yes, there's an unpaired electron. And then we can learn kind of what the sample type is from that G factor, looking at how close or far it is away from 2. And then also we can, from this, the hyperfine splitting, that tells us stuff about the molecular structure. And then the shape of the lines actually tell us more about like kinetics and such. So applications, this can really truly be done on anything that has an unpaired electron. Free radicals, transition ions, point effects in solids, conductive electronic systems. If you have an unpaired electron, you're good to go. So there are a lot of biology examples out there. But if you know me, you know I want to leave the biology to anyone except me. Like I do not want to learn that. I'm not that great at it. So another example I found, which I don't know what this does about me, is the analysis of beer staleness. So here we go. Basically bottling, producing, distributing beer is a little bit of a challenge because we have oxygen in the air, right? And that can get into your product, the can, the bottle, whatever you're drinking out of. And so this oxide free radicals can actually produce beer, stale beer. And so that's why a lot of breweries add antioxidants in your beer to kind of counteract that effect and prolong the time until the beer stales. And so you can use EPR for this, electroparamagnetic resonance, to kind of see how long it takes for an oxide radical to be present in serious amounts. And that would indicate that your beer is staling maybe prematurely or maybe later. So that's what this company did. They looked at the lag time. So how long does it take until we get that oxide free radical in a substantial amount? And so they just compared 4 different beer. They didn't tell me which ones. This is from the manufacturer's website, or else I'd tell you. But we would want to drink or buy the one on the bottom because that has the longer lag time. So this is not my exam question, but it's a quick review so that you go away feeling like you learned at least a little bit of something. So unmute your mic. And for 1, EPR spectroscopy applies a set blank: magnetic field, radio frequency, microwave, or infrared.
Microwave.
Awesome. And a sweeping.
Magnetic field.
Yes. Awesome. So if y'all remember back to the graphs I had, we had B naught increasing with the zoom in effect, and absorption occurs when you get to a certain B naught. Okay. To investigate properties of, come on, you know this. Yeah. Okay. Of open shell systems. So that is a very big picture sentence. And those are my references. Thank you very much. Are there any questions?
I have a question.
Awesome. Let me get to where I can see you.
Oh, okay.
Okay.
So you talked about that samples needed to be at really low temperatures. You might have talked about this and I just missed it, but is the sample under vacuum, or how do you get to that temperature?
Honestly, that's a great question. I didn't read anything in my sources about it being part of the instrument. Like, I know we have that sample cavity, but that's more so to make sure you're getting those microwave wavelengths where you need them and at the correct wavelengths and frequency. I will say it probably, considering you can do so many different compounds, like this is not just restricted to free radicals, right? Like this is anything, like you can have solids or something like that. I would guess it would depend more so on the sample than the instrument. That'd be my guess.
Yeah, so that same summer project where I used AFM, I used EPR. And in the instrument I used, we had our sample, which was on a silicon wafer. That was, I don't know, a centimeter or something square. And we literally just used tape to put it on the end of the EPR probe. And then you put that EPR probe in. And I don't remember if there was like a jacket that had liquid helium in it, or if the probe itself had liquid helium in it. But one of the two had liquid helium, and liquid helium is 4 Kelvin-ish. And so that's where your cooling comes from.
Oh, thank you. And I also had another question just about, I guess, the instrument. So with NMR, we talked about like the sample spins and shimming coils, even out the magnetic field. Are all those things in place for this instrument as well?
I didn't read about it, but that doesn't mean it's not out there.
Yeah, not so much, because the magnetic field is so much smaller, and because the magnetic field is what we're scanning anyway. We don't care so much about getting it to be exactly perfect. We care more about the frequency being exactly perfect, and it's much easier to get a perfect frequency than it is a perfect magnetic field. Before you go potty, I'll tell you a little bit about that project, since both of these people have gone now. It was actually a Defense Department project, and we were making these arrays of magnetic nanorods where the length to width ratio was changing. So they were all 100 nanometers wide, but they were between 100 and 3,000 nanometers long. And they all absorbed different frequencies in the microwave range. And the idea was that you could sort of build an array of these things and then rotate one of the disks, one of those orientation factors out of sync. And because they absorb mostly along the length of the nanorod rather than along the width of the nanorod, that particular microwave frequency could pass through for things in missile communications and things like that. So that was my sophomore undergraduate research project. Okay, go potty. We'll reconvene at 3:45.
That's right. That's me. Okay. I've been on several Zoom classes today, and my audio's cut out sometimes. So if it does that, just someone let me know and I can restart my thought.
Okay.
Okay. Hopefully it won't happen, but we'll see. So as Dr. Davis said, I picked Fourier transform ion cyclotron resonance mass spectrometry, which is quite a mouthful. So FTICRMS, sometimes it's abbreviated FTMS or FTICR. And then this picture is the instrument, and I believe it's, this is from a group at Yale that performs FTICR. But just some general information. It was a technique developed in the 1950s, but really wasn't regularly used for experimental purposes till the 1970s. And it is a form of HRMS, or high resolution mass spectrometry. And then its main purpose is to detect small mass differences with great accuracy and precision using cyclotron frequencies and a fixed magnetic field, which is measured with mass to charge ratios, with this being mass spectrometry. That's what you would expect, and has applications in pharmacological research and drug discovery and development, environmental research, and energy renewal. With energy renewal, because it can detect small mass differences with great accuracy, looking at things like petroleum has a lot of nitrogen and sulfur components over time. So looking at those isotopes is something that I read a lot about. And then in terms of other applications, really big molecules used in a lot of this biological research are often used with FTICR. So in terms of the box diagram, we have our sample that is ionized. I really kept this simple, but I'll get into more specifics later. This technique's just very flexible and has a lot of components that can be switched out. So I wanted to keep this somewhat general. So ionization, there's really a bunch of different ionization techniques that can be applied to this instrument, but electrospray ionization is the most common. And then it goes through a series of pumping stages. So you have things like ion funnels, quadrupoles, but not necessarily how we see them as a mass analyzer in other ways. These are really just to focus the ions and get them at really, really low pressures before they're sent for excitation and detection, which is done in a superconducting magnet. And in that superconducting magnet, there is something called an ICR cell, an ion cyclotron resonance cell, or it's also called a Penning trap, which the ions, when they're sent in there, get excited through pulses with an RF coil, and then are detected. And the signal that comes off those detection plates are Fourier transform occurs. So you get a frequency spectrum, and then a mass conversion is performed to get your mass spectrum. So you can get those mass to charge ratios. And we'll go over all of these specifics later on. This is just sort of the general picture. So in terms of samples, like I said, a lot of like big biological molecules. So like enzymes are really common, and other metabolites. With just things with really large molecular weights are really common. And then it's also really helpful for deciphering really complex mixtures. A lot of the research I saw worked with looking at different matrices that had that worked with metabolomics and lipidemics. And it can also just determine, analyze even just at the 1 to 3 parts per million level. So in terms of ionization, like I said, it's extremely flexible. Different ionization techniques can be used, but electrospray is the most common, which we've talked about. So you have liquid that's sent through this ECI capillary, and when a voltage is applied, it'll generate this aerosol in which the ions can be formed. And what's great about ECI is it can form multiply charged ions, which not all ionization techniques can do. And because a lot of the samples that are typically run with FTICR, it would be great that they can form multiply charged ions. So one of the experiments that I looked at in my research, they were analyzing this really long DNA strand that was in the megadalton range, so just huge molecular weight, and it had 30,000 charges on it, and they were able to, I believe they used electrospray ionization and used ICR to get a molecular weight off that, which was really cool. And then, like I said, other ionization methods can be used. We've gone over some of these in class. I'm not sure if we've gone over all of these, but atmospheric pressure chemical ionization, matrix assisted laser deabsorption ionization, desorption ionization, and then direct analysis in real time, which are all forms of soft ionization. I didn't see any other, I mean, I know some of these ionization, I think, have the option of doing hard ionization, but just from what I could read, I never saw any forms of hard ionization being used in FTICR. And then what's really unique about this process is that the ions are trapped, so they're not destroyed in the process. And so oftentimes other experiments can be followed with these samples. So fragmentation studies are quite common, and then also gas phase reaction studies, so which go into things like the basicity calculations or looking at gas phase kinetics, ion dissociation studies, and then ion molecule and ion interactions are looked at. And so after the sample is ionized, like I said, it goes through these series of pumping stages. And this is just one schematic that I've looked at, but from what I've read, it can be kind of customizable in terms of what can be shown. So there's some ion funnels which focus those ions into a beam. And you have hexapoles, which are like quadrupoles, but just with more poles. And some of these traps, essentially what they'll do is they trap the ions so that they move in this axial direction, because the goal is to get them into the ICR cell. And as you can see, the pressure, I know this picture is not the best quality, but it was really hard to find something that went over all of the optics. And there's a lot of math that goes into this. There was one paper that I looked at that had so much math about even just these transfer optics. It got quite overwhelming. But as you see, we're here at 1 atmosphere, and then slowly we're decreasing our pressure to the point once we get to the superconducting magnet. We're at we're basically under a super high vacuum. Okay, and now the fun part. The ions, once they are put into our ICR cell or the Penning trap, we have this uniform static superconducting high field magnet, which is typically about 4 to 13 Tesla. But there's this FTICR magnet. I don't remember where it was, but it's a 21 Tesla magnet, which I feel like was funny because they talked about how cost effective it would be because they wouldn't need to use it doesn't need to be cooled with any gases apparently. But I just thought that was funny because I figured if it was a much bigger magnet, it must have been much more expensive. But for your typical FTICR instrument, you will be cooling it with things like liquid helium or liquid nitrogen. And when these ions enter the magnetic field, they'll bend and kind of go into this circular motion, which is called the Lorentz force, which just describes that motion of the ions that are in this plane perpendicular to the magnetic field. And something that is measured when the ions are in this magnetic field is called the cyclotron frequency, which just is the frequency of the rotation of the ions, which helps us get that mass to charge ratio. And so we have a few different plates that are used. So there are trapping plates, which aren't shown on this diagram, but they would be at the front and back ends of the Penning trap, just to make sure those ions don't leave. You also have the excitation plates. So an RF pulse is kind of sent through these plates, which so when the ions are put into the trap, they're just in this natural state, this natural spin state. But by exciting them, they will go to a higher spin state, which will move them a lot farther. So they'll be closer to the actual plates and closer to the detection plates. So this RF pulse will spread those ions out, and it will essentially trigger this alternating current between the plates. And so this frequency of this alternating current is equal to that cyclotron frequency I talked about. And the intensity of that current is proportional to the number of ions in the sample. Okay, and so this is sort of what I was trying to talk about with when the ions naturally, when they just enter the cell, they're just spinning, doing their own thing naturally, but once they're excited, they move to a higher orbit. And then when they are detected, so the RF pulse is no longer doing anything, it's now just based on that alternating current. So eventually, because they're no longer being excited, eventually they will return to this natural orbit. And to kind of explain this a little better, there's this if you can't see this, just let me know, but
you're okay.
There's this simulation. Oh, come on, please work. I don't know why it's not. Oh, okay, my computer's just slow. Okay, so this is sort of a demo that kind of shows you how the excitation and detection of these ions work. So right now our plates are all off, but if we excite them, so you can see the radio frequency pulses are allowing these ions to go from their natural spin state to their higher orbits. So we'll just wait for them to start moving. You can play with the applet speed as well. So that's what they look like. And then if you switch to detection, you can see that they're much farther out and are able to interact with those detector plates. And we're able to get our voltage versus time, our time domain graph from that. Oh my goodness, where's my presentation? Okay. Oh, from the alternating current. That's what I was going to say. Okay, so hopefully that kind of helps you visualize the excitation and detection process. So at the end, you saw this time domain spectrum, which is also called the convoluted frequency spectrum. So that just measures the ions and their signals. And so we use Fourier transform so we can understand the data a little bit better, which converts those signals to a frequency versus intensity spectrum. And then using mass correction or mass conversion, we can get our mass spectrum, which will plot the mass versus the intensity of the spectrum. And also a lot of instruments have, they can apply different calibration formulas based on the instrument. There was a lot of, there was a paper that I looked at that did cover a lot of math and calculations for their particular instrument. But I didn't really feel the need to include those. But these were the formulas that I did find the most helpful. But like I said, there was really a lot of different ways I could have gone with the formulas. I just picked the ones that I thought were the most commonly used. So that Lorentz force that I talked about can be calculated using the charge of the ions and the velocity of the ion all times the magnetic field. And then this Greek letter, we typically see that as like the angular frequency, but when you have that C subscript, it would be the induced cyclotron frequency. And if you just kind of rearrange that equation a little bit, you can actually solve for the mass to charge ratio using the cyclotron frequency, which is sort of the general gist of FTICR. And then this is another simulation, but I think it will help you put all the pieces together and kind of see how the instrument functions as a whole. And there's no sound, so don't be surprised if you can't hear anything. So they use, I'm assuming they use electrospray ionization just kind of by looking at it. So you can see there, you have the sample that gets broken up into the different ions. And they don't go really into the pumping stages, or they don't really go into a lot of depth there, but really just the ions are really being focused down and being sent to the superconducting magnet. And so they're in the Penning trap right now. So these two plates to the left and right are the excitation plates, which are being excited by that RF pulse. And once that's been applied, they can be detected off the detecting plates. And you will get your time domain. And then, okay, this takes a second. So you can get that time domain and then use Fourier transform to get that frequency graph, and then using that mass conversion, they actually use that formula. They show the formula for the mass conversion. Oh, okay, come on. All right, so let's look at it in comparison to some other HRMS, or if you don't remember, that's high resolution mass spectrometry. So I want to say for your typical MS instrument, you're looking at resolutions of maybe 30,000, but with FTICR, you can get things up to even greater than 1 million for their mass resolution for an ion whose mass charge ratio is 400. And so we'll look at FTICR as it compares to Orbitrap and time of flight, which I will say was very hard to find advantages and disadvantages for these things, because a lot of their advantages I felt were quite similar. For all of these methods, you could use different kinds of ionization. None of these destroy the sample. But in terms of mass resolution, FTICR really is the best when it comes to having really well-resolved peaks. And then Orbitrap will follow that with, it has really great mass resolution, and then time of flight MS also has high resolution, but just not as high. And then, yeah, they all have flexible ionization options, but FTICR is expensive. It's $1 to $2 million for the instrument, not to mention the upkeep of always having things like liquid nitrogen and liquid helium and just keeping up with the magnet and everything. And this also attributes to slower acquisition rates in comparison to the other instruments, which makes it a little bit harder to couple with things like liquid chromatography and GC. I will say that I read some papers where they still used LC with the FTICR, but it just took longer to run their experiments in comparison to studies where they coupled these chromatic method I can't talk different things like LC with the Orbitrap and the time of flight mass spectrometer. So while you might have faster acquisition rates with those instruments, and they're also cheaper, really just because they don't have a magnet. I think that's just where a huge portion of the cost comes from. And I think that's everything with there. And so in terms of typical experimentation, so using it for mass resolution and mass analysis is quite common, especially for looking at proteins. So it's currently pretty standard to get to perform unit mass resolution and mass analysis with proteins that are over 60,000 kilodaltons, which, if you don't know, 1 Dalton's 1 AMU. And one experiment that I looked at measured the mass of 2 different chondroitinase enzymes. So at the bottom, they talk about, the magnitude of their magnetic field, and you can see these are the 2 different enzymes they're able to pick up, and then at the top, this is the mass resolution for the 91 peak. So you can see the resolution is, for this instrument, was 150,000. And then also, if you just look at the size of the enzyme, it just blows my mind that you have 112.5 kilodaltons in terms of its molecular weight, which is crazy, crazy big. And that's everything. Yeah, I have exam questions as well that I can go over. I can go over them now, or
well, we're running a little long, so let's see if there's any questions for Savannah.
sorry if I took a long time.
It's okay. It's a good topic. I think I told you that this is the technique that the professor at Purdue used to get her $40,000 contract with the petroleum industry.
Very cool.
Yeah.
I had a great time, but I was very overwhelmed at first because it was just overwhelming.
All right. If there's no questions, then we'll move to ion exchange chromatography. Ashley's ready.
That's me. Okay, let me see. I have to figure out how to share my screen. I'm sorry, I have not done this either. Do I need to pull it up from my, I guess I can do it this way. What's the easiest way to do this if I just have it saved as a PowerPoint?
Just go ahead and open up the PowerPoint, and then at the bottom of the Zoom screen, click share screen and choose the PowerPoint window.
Oh, easy, okay. Okay, can everybody see this?
Yep.
Okay. So I did mine on ion exchange chromatography, and this type of chromatography separates ions and polar molecules based on their affinity to the ion exchanger. And so this can be done on a variety of different types of samples, ranging from like large proteins to small nucleotides and even amino acids. And so some of the basics, just like the other types of chromatography that we learned, there's a mobile phase and a stationary phase. And part of the mobile phase includes the elutant. And so this is basically what you would consider to be the carrier of the analyte. And so this is what helps carry the analyte or your molecule of interest through the chromatograph. I'll go more into the stationary phase later, but the basic principle of this type of chromatography is the charged ions in the mobile phase get attracted to oppositely charged ions that are present in the stationary phase. So there's actually two different types of ion exchange chromatography. The first one is cation exchange, and the second is anion. And so for cation exchange, the stationary phase is negatively charged, and so therefore it attracts cations. And then the opposite is true for anion exchange. And so its stationary phase is positively charged, and it attracts anions. So if you look at this graph on the left, you see that pi, and that stands for the isoelectric point. And so at that point, the molecule carries a net charge of 0. And so you can see below that isoelectric point, you're binding to the cation exchanger. And above that isoelectric point, you would be binding to the anion exchanger. And you can see, based on that graph, the stability range for both of them, but we'll go into more depth on that later. So the resin, this is a really, really important part for ion exchange chromatography. And this is what basically constitutes the stationary phase. And so the resin is the physical medium that facilitates the ion exchange reaction. and it's comprised of polymers that form a chain of hydrocarbons. And so what happens is the resin that you choose, it undergoes a chemical treatment that basically inserts functional groups into that resin. And so those functional groups are what provide the charge that can attract oppositely charged ions that pass through in the mobile phase. So the polymer matrix has these ion exchange sites, and the resin is comprised of microbeads that typically range in the radius from 0.25 to 1.25 millimeters. And so these are known for having a really large surface area on the inside and the outside, because that's where the actual ion exchange takes place. And so I'll go into a little bit more depth later, but typical counter ions that are present in these microbeads for anion exchange is a chloride ion. And then for cation exchange, it's a sodium ion. So that means when an ion or an ion of an opposite charge comes in for anion exchange, the chloride ion leaves from that microbead to be replaced. So then there's a few different factors that you have to consider when you're trying to choose your resin for the typical experiment that you're wanting to run. So the first thing to consider is an anion or a cation exchanger. And this has to do with the protein stability. And so some proteins are only stable above or below their isoelectric point and not both. And so this would be a situation where you'd have to decide whether an anion or a cation exchanger fits. But in some cases, proteins are stable both places, so you could choose either one to use. The next thing to consider is if it's a weak versus a strong ion exchanger. And so this has to do with the buffer's pH range. And so a strong ion exchanger allows a wide pH range to be used, whereas a weak ion exchanger only provides a very limited range for the pH. And so most of the time you are going to want to use a strong ion exchanger, but there are times where the selectivities vary for weak versus strong. And so the strong or the weak can sometimes be preferred depending upon what you're interested in. The next thing is the ionic form of the resin. And so like I mentioned earlier, that sodium and chlorine are the most common counter ions. You have to consider the ionic strength of the resin versus what you're trying to isolate. And so that'll play a part in that. Resin particle size and the permissible flow rate kind of go hand in hand. And so typically, if you're wanting a high resolution, you need to use a smaller particle size. But with that, so with a small particle size, you get a higher resolution, but you have to use a slower flow rate, and then vice versa. So if you have a larger particle size, you'll have a lower resolution, but you can implement a faster flow rate through the column. And then the last thing to consider is the dynamic binding capacity. And that basically just kind of talks about how much the resin can actually afford, how much protein the resin can actually bind to itself. So when you're thinking about what you want to isolate, these are all things that you need to consider for your resin. So looking at the manufacturer's website, which was Millipore Sigma, they have two that they were talking about. And so the first one was called a fractogel resin. And so this one basically has a really good accessibility for functional groups to the biomolecules. And so this allows for a tighter binding for those molecules to the stationary phase, and thus like a sharper elution profile. So the result of using this type of resin would be a high throughput and high selectivity with good purity. And so this is, if you're wanting really accurate results, the fractogel resin is a really good one to use, but it is more time consuming and cost consuming. So when you compare to the Eshimune resin, it has rigid base beads that are used for easy packing for the mobile phase into the stationary phase. And so this allows for a high binding capacity and a good pressure flow behavior. So this one typically allows for a faster flow rate. So it's much more time efficient and cost efficient when it's compared to the fractogel, but it's not going to provide as high of a resolution. So it's just depending on what you're looking for when you run a certain experiment. So when it comes to elution, there's two different methods, but the main idea here is displacement. And so if you think about when you have your molecules of interest are bound to the stationary phase, you need to have something run through the column that basically has a greater affinity to that stationary phase. So it allows it to displace the molecules of interest through the column. And so there's two different gradients that you can use. The most common one is the salt gradient. And so this increases ionic strength or salt concentration through the column. And so at a low salt concentration, proteins that have few charged particles, those are going to elute. But if you have something with a high salt concentration, that's going to allow proteins with many charged groups to elute. So just depending on what you want to actually come out of your column depends on how high the salt concentration is when you run through it. The next one, it's not as common, but it's the pH gradient. And so this goes back to that idea of the isoelectric point. And so the big idea here is that whenever your molecule or your protein of interest reaches its isoelectric point, it no longer has a charge. And so as soon as it loses its charge, it's no longer attracted to the charged stationary phase. So for an anion exchange, since that happens above the isoelectric point, decreasing the pH will allow that molecule to elute. Whereas if you're in a cation exchange, because that binds below the isoelectric point, if you increase the pH, that'll allow your protein to elute out. So it's this idea of you want to increase the affinity. You want to have something that it has a greater affinity to the stationary phase so that it displaces what you're looking for and it can come through the column. So here are a few parts explained when it comes to it. So the injector, you have to have, it has to be liquid, it has to be in the aqueous phase. And so the liquid can be directly injected, whereas if you have a solid that you're wanting to run through, it needs to be dissolved before it can be injected. So the sample range can range from 0.1 to 100 milliliters. And this just allows for a high reproducibility. And it also does have to be under high pressure around 4,000 PSI. The column, this can be made of a variety of different materials. So you could have stainless steel, titanium, glass, or inert plastic. And the diameter of this can vary between 2 millimeters and 5 centimeters. And then the length can vary between 3 centimeters to 50 centimeters. And so then there's another aspect that you can have a guard column, and this comes anterior to the separating column. So this just helps clog, like filter out clogged particles or anything that could create noise and take away from the signal in the column. I don't know why. Okay. So then for the detector, every single thing that I found was an electrical conductivity detector. I would say that it was definitely the most common, and that's because it has the greatest sensitivity. And so that's really important when you're trying to look at affinities and attractions and stuff like that. But a few other types of detectors that could be used is a UV detector, an electrochemical detector, or a PDA, photodiode array detector. And there were a few other ones, but honestly, I only ever saw the electrical conductivity detector being used for this. So here is a block diagram of what an instrument like this would look like. And so you can see in the one on the left, it says mobile phase reservoir. On the right, it says the elutant. And so that gets pumped up. So that pressure pulls up that elutant through the pump, and it's put into the sample loop. And so it'll either go through whether you're running an anion exchange column or a cation exchange column. And you can see down there at the bottom, you would inject in your sample. And so that gets run through the column appropriately, and then it'll reach the conductivity detector and then data processor. But the one on the left, it includes the suppressor column. And so what that's used for is to cancel out any noise. And so to basically, it removes all but the analyte atoms from the phase. And so you're no longer looking at anything. Nothing else is giving off a signal that you don't want after it passes through the suppressor column. So some advantages and disadvantages of ion exchange chromatography. This is especially compared to an HPLC, although they can be used together. There are some advantages and disadvantages here. So ion exchange is highly selective because you're looking at affinities between ions of opposite charge. And so they're very attracted to one another, especially as they pass through the column. Another advantage is that with this type of chromatography, you can have a really high flow rate, which makes it efficient. But like I mentioned earlier, it comes at a cost. So if you do have a higher flow rate, typically you will have a lower resolution. It does provide a high yield. And then the buffers are non-denaturing, which means nothing is structurally altered as it passes through the column. And so that's a really good benefit, that nothing that you're experimenting with is denatured. Some of the disadvantages is that the sample must be loaded into column at a low ionic strength. And this is because the stationary phase is charged, whether positively or negatively, depending upon which type of exchange you're doing. But if you have a bunch of ions, strong ions in there, it's going to be attracted to that, opposed to the ions of interest or the molecule of interest that you're trying to look at. So something that can happen is a cluster of positively charged residues can cause a negatively charged protein to bind to a cation exchanger. And so if you have these other ions in solution, sometimes things can bind to the wrong thing. Instead of the molecule of interest binding to the stationary phase, those ions can create their own cluster and cause their own attractive forces. And then one thing that's really important is that any change in pH, no matter how small, can greatly affect the binding profile. And so this is kind of going back to that image that I showed of the on the cation and anion exchanger page, but especially with proteins, like they can have a positive, negative, or a neutral charge. And so any change in the pH can cause drastic changes in the molecules and the proteins that are being run through the column. So you just have to make sure your buffer maintains a really stable pH throughout. So one of the most common uses for this is protein isolation and purification. And just like I kind of mentioned, proteins are made up of amino acids. And so some amino acids are have a side chain that's positively charged. Some have a side chain that's negatively charged, no charge, and vice versa. So a common way to isolate a protein and to purify it is using a sulfonated polystyrene resin and HCl as an eluent so that it evaporates and it's an easy eluent to use. But if you were to look at lysine, arginine, and histidine, these are all positively charged. And so a cation exchange would be good for them because they would be binding to that negatively charged stationary phase and allowing everything else that's not of interest to pass through. And then an anion exchange could be used for aspartic acid and glutamic acid because those have negatively charged side chains. And so those would be attracted to that positively charged stationary phase. So that's a really common use for this kind of chromatography. And then these are my test questions. I can go ahead. Do you want me to go ahead and say the answers to this?
It's up to you.
Okay, I'll say it real quick. How many types of ion exchange are possible? There are 2 types possible, anion and cation exchange. And then what is the purpose of the chemical treatment applied to the resin? The chemical treatment is what inserts the functional groups into the resin that allows for the positive or negative charge to be present in the stationary phase.
All right. Well, I don't know how they've managed it, but Annabelle and Ashley are going back to back in alphabetical order. Ion exchange, followed by scanning electron microscopy. It's a big jump in the alphabet, but they managed to go back to back here. You ready, Annabelle?
I reckon.
All right.
Alrighty. So I did scanning electron microscopy. And so what is it? It can scan areas of 1 centimeter to 5 microns width, has a big range of magnification and spatial resolution. And so what happens is an electron beam is applied to a surface of a sample, and then that forms an image based by scanning the electron beam at particular locations on the surface. And at the bottom here, this is an instrument made by Nikon. So a familiar imaging company makes this scanning electron microscope. So here's my block diagram.
So what happens is an electron beam is produced by an electron source, and then it goes through condenser lenses, and then a scanning coil, and then the objective lens. And the scanning coil controls the rastering of the beam so that the beam can scan different parts of the sample. And then the SEM collects the electrons scattered off the surface. So that's what the detector is doing. It's collecting electrons that are bouncing off. These can be different types of electrons. Some are called backscattering electrons, secondary electrons, and auger electrons. And secondary electron detection is the most common, and it uses a detector similar to the one we saw in UV-Vis, the photomultiplier tube with scintillators. So, and it's also in a vacuum. There are two, like some are high vacuum and some are low vacuum. The more common is high vacuum because the low vacuum, that's for like special samples. So here are a few schematics that I found online. And you can see that it gets a little bit, like this one on the right, is a little bit more complicated, but we can see that there's different detectors. So this is an X-ray detector. Here's the secondary electron detector on the left. But it pretty much has the same general setup with your source and then the lenses, the scanning coils, another lens, and then the sample and detector. So there are different types of sources. The one at the top here is a tungsten filament. And so this is heated until it emits electrons. So it has to get really, really hot, which means that this filament will eventually evaporate. So it can be used for about 100 hours, depending on which vacuum it's in. And then this one in the middle is the field emission gun. This is the best choice for SEM because it generates a really high resolution, but it's really pricey. And then this last one, the cerium hexaboride cathode, shown at the bottom, is really bright. So it's like 10 times brighter than the tungsten filament. And it also lasts 15 times longer. So it's used in a lot of instruments too. So sample prep. In this instrument, the sample must be solid, but it can be at any thickness. So it also requires that the samples be conducting. So sometimes if you have an insulating sample, they will sputter coat the sample with like a metal or some other type of element. So like if you're wanting to analyze the elements, you'll use a carbon coat. But if you want like a really good image of the sample, you'll use a metal coating. And shown here is a spider that they sputter coated with gold, which I thought was pretty cool. And then here's some advantages and disadvantages. So it's really good for solid materials. It has many different applications. It's used in a lot of different fields, easy to operate. Like there's little to no sample preparation. That just depends on what type of SEM you're using, because if you're using like a low vacuum or an environmental SEM, it'll take more sample prep because those are more difficult samples to scan. It's fast and it produces data in digital formats that are highly portable, but it being solid can also pose a problem. Not everything that we want to look at is solid, and it also has to fit in the microscope chamber. They have to be stable in vacuums. They can't be wet. And then it's not very sensitive. So if there's like really light elements or trace amounts of elements, it probably won't pick up on it. And then you need that conductive coating if it's insulating. And so now comparing it to transmission electron microscopy, these are really similar, but with transmission, the electrons actually go through the sample instead of just going on the top and then electrons bouncing off. So TEM samples have to be really thin because they have to actually go through the sample. But the magnification for TEM is better, has a greater resolution. But yeah, SEM is better for surface analysis, and it gives a 3D image as opposed to TEM, which gives a 2D image. And then what is it used for? Like I said earlier, it has a wide range of applications. And some are shown. So material science, understanding nanowires, quality control of semiconductors, microchip design. This is pretty cool. I mean, just thinking about all the technology that we use on a daily basis, the SEM can be used to analyze these microchips and make them better. And then forensics, which I'm going to go into a little bit more than in the biological sciences. So it can look at soil and rock samples to tell you like what is the structure of these things and what is the actual elemental composition. And then medical science and art. I actually looked at a few different images of the of art created by SEM. And some of it's actually pretty expensive, but it's all really cool. So in forensics, electron microscopy can be used with microtrace evidence. So they find microtraces of like glass or paint fragments, tool marks, drugs, explosives, and gunshot residue. And it can be visually and chemically analyzed with the scanning electron microscope. And so shown here is actually gunshot residue that they were able to determine that it was from a 9mm gun. And yeah, so that's about it. And there's my sources. Any questions?
All right. So you talked about the Auger electrons, the Auger electron. Those, how do those differ from the backscattered electrons?
I actually am not completely sure. I only really looked into the secondary electrons because that was like what they most commonly measured. But those are just like the electrons generated because of the ionization of the sample. So I didn't look into, what'd you call them? It's not auger.
Auger, I think it's supposed to be French.
Mm.
Yeah, so I think, if I remember correctly, that the Auger, the secondary electrons are from the valence shell because they're the ionizing electrons. And Auger electrons are when you remove a core electron. And so I think that I'm pretty sure that's what Auger electrons are. And that helps with your elemental determination because the energy of that Auger electron helps determine sort of how deep in the core it is. And that's going to vary based on the different elements. All right, well, last but not least.
All righty, let me share my screen. All right, are y'all seeing like the subtitles down at the bottom? Y'all see any of that?
Whoa,
Yeah.
how'd you do that?
I don't know. My computer just automatically does it. Oh well, I guess we got subtitles. So what my project was is I focused on X-ray fluorescence, and specifically I mostly focused on handheld X-ray fluorescence. So in general, there are two main different types of X-ray fluorescence. There's wavelength dispersive X-ray fluorescence and energy dispersive X-ray fluorescence. And so what I focused on was energy dispersive X-ray fluorescence, which is here on the right. And this is the more modern instrumentation. But the wavelength dispersive, basically, I'll get into more details of how everything works. But after it hits the samples, X-rays are emitted, and it uses the wavelengths of these X-rays to determine elemental information. And the energy dispersive uses a detector and detects energy. So going forward, just X-ray fluorescence in general, it's used for chemical analysis of rocks, minerals, sediments, fluids, and really anything that you want to know elemental information about. Pretty much there's always relatively low sample prep, and just a basic idea of how it happens is you excite a material by X-rays, and the material releases energy, and this allows for detection of abundance and identification of elements. So handheld X-ray fluorescence, these devices provide on-the-fly screening for elemental information. And the biggest advantage of handheld devices over their laboratory counterparts is that they can screen for almost any element in the periodic table and provide results in just minutes or less. And they, again, require very little to no sample prep. And some of the figures of merit is that they're rugged and portable. And I'll explain this later, but traditionally, handheld X-ray fluorescence devices, they struggled with accuracy, precision, and selectivity and sensitivity. But that is improving. That's improving, so that's why I included it as a figure of merit. So on the next slide, I'm going to go through a step-by-step of how these devices work, but this is just general ideas so y'all can kind of follow along better. What these devices are doing is they measure the fluorescence X-rays or secondary X-rays emitted from the sample after being excited by the primary X-ray. And so each element produces a set of fluorescent X-rays that are unique to that element. And so from those unique fluorescent X-rays, we can identify the element. And we can get both quantitative and qualitative information about the elements. So can y'all see my mouse? All right, so starting off, there's an X-ray source. And so what happens is this X-ray source it's pointed at the sample. This is the sample. And what it does is it ejects one of these inner shell electrons. So the inner shell electron's ejected. And then what happens is this outer electron falls down to fill the vacancy of the inner shell electron. And as it falls down, it causes fluorescent X-rays to be emitted. So these fluorescent X-rays enter this detector, causing electronic pulses. And these electronic pulses are sent to the preamp. The preamp magnifies these electronic pulses, sends it to the digital signal processor, and then this sends the data to the CPU. And then this is where you can get your all of your data from the device. And this is just a general schematic from a manufacturer, Thermo Fisher, and this is the general schematic for how all their handheld devices work, but this is pretty much how every X-ray fluorescent handheld device works. So, and then how do they generate these X-rays? I thought that this was pretty cool. And so the device that I showed on the previous page uses americium-241 to produce X-rays. It decays by alpha emission, releasing gamma rays, and then the benefit of using americium-241 is that it has a half-life of 432 years, so you never have to change the source in these handheld devices. And this source is also very robust, and so it allows this detector to identify up to 40 different elements. And these handheld devices are mostly used in geochemical research and an antiques marketplace with this specific type of X-ray generator. All right, so some of the concerns with these handheld devices, the biggest concern was that their accuracy and precision and sensitivity was kind of lacking. But I read a study that used a handheld X-ray fluorescent device, and the name of it's right here, the Bruker Tracer. And basically, they were trying to detect levels of mercury at a site. And what had happened was the calibration curve that was programmed into the device was not really good for the site that they were at. So what they did is they developed a site-specific calibration curve. And what they did was they took like 30 to 50 samples and sent it to the lab to a benchtop X-ray fluorescence detector, got a calibration curve, and then put that calibration curve into the handheld. And what they found was that it had comparable accuracy, precision, and sensitivity to the laboratory devices. And so this study was promising because instead of just using what's pre-programmed in the handheld device from the manufacturer, if you can take time to make your own calibration curve, then these handheld devices can be pretty much just as good as the big expensive ones in the lab. But the downside is that to get the benchtop performance out of these handheld devices, you have to take the time to make your calibration curve. Some applications of these handheld devices. Traditionally, they were mostly used for only identification of metal alloys and detection of lead-based paints, but it's expanded incredibly. Pretty much any field that you want to know if there's elements in something, you can use these handheld devices, like screening for toxic elements in foods, screening of mining ores, agricultural soils, geological samples, and dust and air samples. All right, so just to recap, some advantages and disadvantages of these handheld devices. They're really good for elemental detection. You can get quantitative and qualitative information, so you can get amount of elements, and you can get what type of elements. They're quick on-site data, and with the proper calibration curve, they're just as accurate, precise, and sensitive as the big laboratory X-ray fluorescent detectors. They're rugged and portable, little to no sample prep, and you don't have to destroy the sample, which is really important. You pretty much just stick the handheld device up to whatever your sample is, and then it gives you the readout. And they're cheaper. But the disadvantage of these handheld devices is that they can sometimes require a calibration curve to be as accurate. And there's a specific range of elements that all of these devices are good at detecting. And so some of these handheld devices are not really good for detecting elements with an atomic number of less than 11, but the range of what elements the detectors can detect is based off of the device itself. And one of the downsides to X-ray fluorescence in general, not just the handheld devices or the laboratory devices, is that none of those can distinguish between isotopes of the same element or ions of the same element. And then this is what a benchtop X-ray fluorescence device looks like. This is pretty top of the line stuff, and because you can get quantitative and qualitative data, just like the handheld device, but you can get a lot more accurate quantitative readings, because what happens is up here in this little sample tray, you put really specific amounts of samples in, and so you can really get super specific concentrations and really know how much of an element that you're dealing with. And they have the highest precision and accuracy and sensitivity, but they still can't distinguish between isotopes or ions. And one of the main differences that I saw was that these benchtop fluorescent devices have what's called a polarizer in it. And so once the X-rays hit the sample, they can become polarized and they scatter some. And this polarizer basically reduces the scattering, so as much of your information goes to the detector as possible. But yeah, I mean, the benchtops are incredibly good, but what I thought was interesting is that the handheld devices, when you put the correct calibration curve in, are pretty much just as good as these benchtop versions. And then my exam questions was, what type of wave does the detector analyze in a handheld X-ray fluorescence device? And that would be the fluorescent X-rays. And then how do you prepare the sample for analysis with a handheld X-ray fluorescence device? There's really no sample prep. And then there's my works cited. So yeah, that's it.
All right, any questions?
Yes, I have two. The first one is, you talked about how it basically like ejects a core electron. And for some atoms, there's a whole lot of core electrons. So like, is there any variation based on like how deep into the core it goes, or is it specific about like staying in the outer core, or does it not really matter? It's just not a valence electron. And then to kind of go off of that, like what exactly is being detected? Because I missed that.
So I don't know I was kind of confused about that, but I couldn't really figure it out. I don't know where the threshold is of how far in the X-rays penetrate into the orbit, and how it determines like which electron it's going to eject. But what it's doing is it's giving us elemental information. So it's telling us what elements are present in a sample. So it tells us what elements are present, and then also how much of those elements are present. And it's doing that by once it ejects that inner electron and the other one falls down into that shell, and releases those X-rays, and it's measuring them. But how it does that, I had no clue.
So my guess is that as you go deeper into the core, it takes a lot more energy to pull those electrons out, right? And so my guess is it's going to be the N-1 shell. It could be the N-2, but again, because these are atomic transitions, they should have very, very narrow bandwidths. And so, let's talk about sodium for a minute, right? We're pulling off a 2 N=2 electron and replacing it with the N=3 electron. And that delta E is known. And we can probably say with some certainty that it doesn't overlap a lot of other metals, just because those transitions are so narrow. And if there is an overlap, then that's just something that they have to work around. Anybody want to say why maybe you can't detect anything lighter than sodium?
Will it take a lot more energy to remove those electrons?
Yeah, the only electrons that are core are 1s electrons. And those 1s electrons are so close to the nucleus. Golly, it just takes so much energy. Yeah, absolutely. Okay. Excellent, good stuff.
But would you use the same, just think of like the biggest element, right? And then an element in the second row. Like that N-1 electron from the heaviest element is going to be a lot easier to get off, right?
Sure, absolutely.
Second row. So do we change our energy? Do we change our...
So it's probably a lot like UV-Vis in that there's no monochromator on the X-ray instruments. And so you're probably just bombarding it with all of this light. And yes, there's some really high energy stuff. And you likely do pull out some N-2, N-3 electrons. But hopefully you also pull out an N-1, and that's likely what is detected. I mean, on most of these instruments, you can probably pull out the spectrum if you really wanted it. But they're calibrated so that they know if it's this wavelength, then that's going to be aluminum. Okay. All right, we're nearing the finish line. Any questions about how the rest of the semester will play out?
So we're coming to class on Friday, like on Zoom to take the quiz.
I'd like to. I mean, the quiz is going to be on Moodle.
Okay.
I'd like for us to meet together on Zoom. Like I said, it's only going to be 10 questions. And as long as you've done your homework, you can just upload your homework and not answer those 2 questions. The homework submission, I think, is up already. I haven't checked to see if anybody's uploaded it. If you did not have your exam questions as part of your PowerPoint slides, please send those to me so that I can pick one. Okay.
Do we need to send them to you even if they were in our PowerPoint?
No, I'll just go back through the recording and check out those.
Okay.
Dr. Davis,